Good morning, everyone. I hope I'm clearly audible. Welcome to the Introduction to Quantum Computing workshop. We'll get started for today. We were waiting for about 5 minutes to give some more time. We still see people joining, so hopefully the others will join as we continue. So without delaying any further, we'll get started with today's proceedings. To kick things off, we have Dr. Ranga Rodrigo, the head of the department at the Department of Electronic and Telecom Engineering at the University of Moratuwa. He'll be making some initial remarks. Dr. Rodrigo, I hope you can hear us.
Yes, Dr. Charles, so thank you very much for allowing me to speak at this very important start of the session on quantum computing. So as you know, the quantum mechanical phenomena like superposition and entanglement is used in quantum computing, and it can have the potential to become extremely efficient and fast. Starting with extremely difficult experiments now, it is at a position where we also can experiment ourselves. Also, the applications are there in using this for machine learning as well. So with this background, at the department, we thought that it is essential for us to think about this extremely powerful area and slowly develop expertise in that area. In the department, we start areas with seminars like this, and then slowly we introduce final year projects, and then perhaps subjects, and then we would be able to start research areas and send students in these areas to be able to do research as well as for even employment opportunities. So identifying trust areas in this context is extremely important. So when we identify a trust area, we have to procure the expertise from outside. So this is why I'm very thankful to this eminent panel that we have today. For some of them, it's tonight. Dr. Harini is there, and Mr. Kithmin, then Mr. Ravi and Ms. Teshani are here in this forum, and Dr. Charles is organizing this. I'm very thankful, and I welcome each one of them. Mr. Kithmin is joining from Canada, UBC, and Teshani from US, Dr. Harini and Ravi from Australia, and we are joining from Sri Lanka. So it's the concept of our friends and alumni helping each other for a very important course here. So thank you very much for joining. I'm very happy that many people have joined this meeting so that you can gain insights. So initially it will be a simple description starting with the keynote address by Dr. Harini Hapuarachchi, and then afterwards we will go into the basics. I think Kithmin will describe that in detail, and maybe you will have hands-on experiences in the afternoon. So thank you very much for joining this. I wish you good deliberations throughout this session. Over to you.
Thank you, Dr. Ranga. Right, so as Dr. Ranga mentioned, as a department, when we venture into new areas, we have to get started somewhere. So this is one such attempt. And there was a reason for us making this open to the general public as well. So this workshop goes out to everyone, not just to ENTC students. And the reason for that is a few steps that we have taken along the way. Before we go into quantum computing, we thought that we will give that brief overview to you. So let me share some slides. All right. I hope you can see the screens with the slides. That happens always sharing a different screen. So just wanted to make sure. Yeah.
Yes.
Thank you, Kithmin. Right. So we've actually done similar workshops and short courses in the past. We wanted to give you a bit of the motivation why we have done this. That all started when Kithmin, two individuals, actually Kithmin and Abba, who graduated from ENTC, we had a conversation about organizing or covering areas that are not covered in the university curriculum. So back then, Kithmin and Abba, they were calling it the missing semester. This is how it all started. So I'll take about 10 minutes to give like a brief history of what happened and what we have done and where we are right now and what we have planned for the future. So Kithmin and Abba, they worked on this missing semester initiative. The idea was, when we go through the university curriculum, of course, the curriculum is not something that gets updated every month. It has a cycle of about 3, 4, 5 years. And then to identify things that we can include into the university curriculum, we wanted to make sure that we look at the latest technologies and we get the industry experience as well and introduce things that are relevant but not yet included in the curriculum, with the plan of including that in the near future. So you might even have heard of this word missing semester from other universities, like top universities like MIT, for example, has a missing semester initiative. So that was the motivation. Through this, we tried to identify what else can we teach to the students. With that motivation, we first put our heads together and then try to identify a few areas that we can address based on the expertise that we have as well. So with that, we started, this was in 2021, we started the Embedded Systems Workshop for Beginners. So few individuals got together, Kithmin Abba and myself and few other undergraduates, Deepana, Shaluta and Dilanka from ENTC, where we delivered an Embedded Systems Workshop in mid 2021. So this was a 4-day workshop conducted over 4 weekends, and we covered things from basic programming and then PCB designing and then some advanced concepts as well. So this was done entirely free of charge, and we got a very good response from the people who took part. And then with that, we thought that, okay, this was a public event, by the way. This was not only for the department. Then we thought, okay, there's a demand in this area. Maybe we can do something that can be productive for other university students as well, because some of these concepts, they are taught at ENTC, but maybe not at other institutes. Then we wanted to scale this up in the sense, bring it up to the level of a semester's worth of material. Like you are familiar with the semester concepts, I'm sure. Then that is about 16 weeks of lectures. Then you get a substantial amount of information when you go through a given course. So with that, we partnered with the American Center in Colombo. This is part of the US Embassy. Then we conducted what we call the Kickstarter on embedded system design. So this was a 12-week workshop series where we partnered with the E-Club at ENTC and the IEEE SL Inspire event as well. We got the financial backing of the American Center in Colombo. So we are quite grateful for their support. The reason for that is, of course, when you go for a 12-weekend workshop opposed to 1, 2, 3, or 4, then the amount of time that people can volunteer is limited. So with the financial backing, we were able to get more lecturers on board. So then that is how we conducted the second workshop. Then we thought of developing a scalable model in which we cover material that is cutting edge, that is quite relevant to the Sri Lankan industry, that can help the public as well. When we were creating courses, these were the values that we wanted to go after. We wanted to develop relevant, high quality content. So what we're trying to say here is, if you go to a website, there are many online materials available that you can learn, right? Because right now in the information age, the problem is not lack of content. The problem is how to find the quality, relevant content among all the noise. That is what we wanted to address. And the second thing is, we did not want to produce another Me Too product. For example, we did not think of developing content for machine learning because if you go to a website like Coursera, there's a very popular course in machine learning done by Professor Andrew Ng. So that's a very prominent course. So as long as that machine learning course is out there, we did not want to teach the basics of machine learning, because then it will be another Me Too product, and we might not even do a good job as Andrew Ng. Right? He's a very prominent figure. Then the third point, we wanted to develop courses with hands-on experience, and we wanted them to be outcome-oriented. So what we tried to achieve here is that one thing that we noticed even within ENTC, in some of the courses that we are teaching, we go in a very theoretically oriented approach. That has its own merits. For example, we can do research when we have a very thorough understanding of the fundamentals. But our purpose was a little bit different. We wanted to give training on subjects to people so that they can do something in an outcome-oriented manner. They get in a way, a vocational training kind of thing where they can contribute to their current job position. So the goal is not to be very research-oriented, but mainly to be from a more from an engineering kind of approach. That was the motivation. So for that, what we did was, when we were developing the courses, we first identified a project. What is the outcome? What will the students be able to do at the end of following the course? Then once we decide on that project or the outcome, we worked backwards. We created content backwards. We decide on the project, and then we start thinking what theoretical aspects should be covered to achieve that objective. So that is, at some point we started calling it the inverted semester as well, because we start from the project and work backwards. And the response we got for some of the courses that we conducted has been quite good. People liked what they were learning. At the end of the course, at the end of 14, 16 weeks, they were able to actually build something, right? So we simplified things. We started from the very basics and then worked our way forward. So these are the current focus areas that we work on: Internet of Things, computer architecture, and cybersecurity. So it's still early days. We are still developing content for some of the courses. This microcontroller-based embedded system design course is currently ongoing. This is the second iteration of the course. We have actually arrived at week number 12, if I'm not mistaken. We'll be finishing this course off soon. We also conducted an embedded machine learning for edge computing course. This concluded about 2-3 months ago. This again comes under the Internet of Things track, if I may call it that. Here is a group picture of a part of the students that took the embedded machine learning course. We did the last session in person at the department. So this is not only for University of Moratuwa students. This was open for the general public as well. And right now we have registrations open for a course on System Verilog. For those who don't know what System Verilog is, it's a hardware descriptive language, comes into the domain of processor design. So we don't assume anyone to know processor design. You can see here the prerequisite is basic knowledge of programming in any language. So if you have that background, and if you would like to get started in the domain of processor design, we are putting together a series of courses. We call it Build Your Own CPU, where we start from this course number 1, System Verilog for ASIC FPGA design and simulation. Once we are done with this, we'll move on to the second and the third course. At the end of the 3 courses, a person will have a very good understanding of how to start from scratch and then build your own processor. Then in May, in about 4 months' time, we'll be releasing another course, Embedded Product Design for IoT. So currently we are developing content for this. This will be building on top of the basic microcontroller course that we have. So that's a quick overview of what we have done so far and what we have planned for the future. Throughout the journey, we have had help from multiple organizations like Synopsys, who partnered with the System Verilog course by giving licenses for their Synopsys tools. They're like they are like multi-billion-dollar licenses, but the company was generous enough to partner with ENTC and provide these licenses to the people who are taking the course. And special thanks to the UBC Quantum Club, who is partnering with us for this particular workshop for Introduction to Quantum Computing, and then for IEEE Sri Lanka Section as well, who came on board as a strategic partner to spread the news and also to give membership benefits to the IEEE members as well. So that's the brief introduction that we wanted to tell you what we have done so far. With those courses, we actually branded as SkillSurf, and we have a separate website for that. You can go here and get to know some of the other things that we do. So the goal is to empower Sri Lankans to be industry and life ready. So this is going beyond ENTC, where we make these resources available to the public as well. So that's the brief summary of what we have done so far, which brought us to today's workshop, quantum computing. This is a new domain for us as well. New domain for us in the sense for SkillSurf. This is the first workshop that we are doing, but definitely not a new domain for the panel of lecturers that we have. They have done a lot of work in this area. So there's a good set of resources for you to learn a cutting edge technology and get started in this domain. So that's it. Let me now hand over the proceedings to Dr. Harini Hapuarachchi, who will start off with the keynote on quantum computing. Dr. Harini, I hope you are there.
Hi, thanks, Subodha. Let me share my slides. I hope everyone can see that.
Okay, for me, it says started screen sharing. Okay, now it's visible.
Are you guys still there?
Yeah, yes, we can see it now.
Okay. Hi, everyone. Hi, everyone. Can you see my slideshow still? I'm sorry for the slight interruption.
We can see it. Yep.
Cool. Hello, everyone. My name is Harini. I did my bachelor studies at University of Moratuwa. I suppose, like most of you here today, I'm now working as a research fellow at the RMIT University in Australia. I'm focusing on quantum sensing as my research focus started quite much on quantum computing. So I'm hoping to give you a bit of a brief overview on quantum technologies and try and set the stage for the rest of the workshop. So let's get started. So let's first try and recall some high school physics first. I hope most of you remember the photoelectric effect. Now, if you take a metal plate, keep it inside a vacuum tube, and hit it with some low frequency light, we're probably not going to see any photoelectrons coming out. Now, classical physics suggests that if we hit it with a stronger intensity of the same light, we're going to see some electrons ejecting. But scientists have tried that, but this did not happen. But if we hit it with a stronger frequency instead, say with violet light, photoelectrons will come out. And the number of electrons that will come out will be proportional to the intensity of the light. And scientists in the 19th century were desperately trying to explain what was going on here with classical physics, but they failed to do so. And in the early 1900s, Einstein wrote Max Planck's equation, this one, if you remember, and tackled this mystery. Light comes in packets, as we all probably know now, or quanta. And this is an important concept in quantum mechanics. And this explanation by Einstein is one of the most important milestones in quantum physics. But if we take a beam of light or many photons together, we can explain their collective behavior using classical physics or Maxwell's equations. And if we go dimming this beam of light, like until we have just one or few photons, we will have to use quantum mechanics to describe how just one or few photons behave. Like this is how we go from the classical to the quantum regime if we consider light or energy. Now let's shift our focus to matter. If you take a piece of semiconductor, a piece of bulk semiconductor, its conduction band and the valence band will be continuous in energy, like I have drawn in this figure here. Now, suppose you hypothetically go crushing this piece of bulk semiconductor into smaller and smaller and smaller pieces until you turn every piece into like nanoscale dimensions, or you turn every piece into a semiconductor quantum dot. Now, when you do this, the conduction band and the valence band will have discretized energy states that look more and more like those of a single atom. Now, the example that I've taken here, the semiconductor quantum dot, is an example of what we call a quantum emitter. Quantum emitters are types of nanoparticles that can absorb and emit single photons, and they can create types of excitations in matter called excitons. It's something like this. They can take in single photons and create excitons. They're like electrons coupled to vacancies or holes that are left behind by the electron that jumps to the conduction band down in the valence band. Now, this electron can jump back down to the valence band and spit out the photon that it has absorbed. What I want you to take away from this slide is that quantum emitters can absorb light and they can emit light back in form of photons, like one chunk at a time. And there are many, many fascinating ways to engineer the properties of quantum systems. And this one is one of my favorite examples. Now, this is a set of quantum dots. Now, if you take a set of quantum dots made of exactly the same type of material and just go changing their size, they will glow in different colors. And that's because the band gap, or the distance between the conduction band and the valence band of these quantum dots, depend on the size of the quantum dot. So the energy of the photon that can be absorbed by that quantum dot depend on the size of the quantum dot. And that's why they glow in different colors. And many technologies are emerging to use engineering capabilities like this one to our advantage. Now, before we look a little bit into different quantum technologies that can be used for our advantage, let's try to get an idea how to use, how small a typical quantum system can be. Now, a typical quantum dot, for example, if you take a quantum dot again as an example of a typical quantum system, it can be about 10,000 times smaller than a human cell. And it's in the same length scale as a protein or a DNA. So we can attach proteins and DNAs into particles like quantum dots and send them inside cells to perform various tasks. And here's an actual transmission electron microscope image where a quantum dot is tied to a gold nanoparticle using a DNA strand. Now, you can't actually see the DNA strand here, but you have to take my word on that because this molecule was synthesized and this image was taken by my friend and collaborator, Dr. Anna Missa, in a project we did together in our current research center, Excitant Science. And there are lots of research that look into the possibility of using quantum emitters and their composites for many different types of diagnostics. And the abstract, very, very abstract idea is something like this. And suppose you have a patient with a tumor. We can inject different types of nanoparticles into the patient, and these nanoparticles will circulate around the patient's body and finally go and accumulate in the tumor. There are different ways to make sure that this happens, reported in the literature. And after these nanoparticles go and accumulate in the tumor, you can shine a laser from the outside onto the tumor and image the tumor or measure different things about the tumor using the emitted photons. But I also should tell you that these technologies are still at very, very early stages of development. And people have tried different things on things like cultured cells and mice, but I'm not aware of any actual clinical studies that have been done yet. And here's another example of a quantum technology. They can be used for solar energy harvesting. For example, you can use them to capture sunlight and create excitons, and you can then transport them using some medium to, for example, a p-in junction, where the particle, the electrons and holes can go sideways, and you can use those charges to create electricity or to get different tasks done. This is a very abstract idea again. A lot of work goes into each and every step in reality. So that's just to give you a bit of a flavor of quantum technologies. There are virtually countless applications of quantum systems, ranging from different types of sensing and metrology to communication technologies. And one day is not actually enough to keep talking about each and every one of those. So let's now have a look at today's topic. Quantum systems can be used to perform computations because they can host the basic unit of quantum information, which I suppose most of you know as the qubit. A qubit is the quantum equivalent of a classical bit. And what's a little bit stranger than a classical bit about a qubit is that it can simultaneously exist in both states, 0 and 1, until you measure it. And what you see here is a block sphere. It's a special tool that you can use to visualize a qubit. You'll learn a little bit more about all these things later today in the sessions. I'm just trying to give you a little bit of an overview of the basic ideas regarding a qubit. And you can perform operations on qubits using what's called quantum logic gates. They're the quantum equivalents of the classical logic gates, and you can put quantum logic gates together to build what's called quantum circuits. And you can put quantum circuits and all these things together to build a quantum computer. Okay, so some of you might be wondering, but we already do have classical computers and they can do many computations fairly well. Why should we care about quantum computers? We care about quantum computers because they may perform some computations better than classical computers, especially those of quantum nature. So quantum computers could someday help us simulate things like very complicated molecular structures and do discovery of drugs much more efficiently than we could possibly do today with classical computers. And the idea of using quantum systems to simulate quantum systems was first proposed by Richard Feynman back in 1981 in one of his famous lectures, and this quote is from that lecture. But building such quantum computers and achieving so-called quantum supremacy is an incredibly difficult task for many reasons. When I say quantum supremacy, it refers to demonstrating that a quantum computer can do a certain task, which could even be specifically selected to demonstrate that it can perform fairly well compared to a classical computer, that it can, a selected task much faster than it is practically possible on a large supercomputer. And Google claimed that they demonstrated this, that a large supercomputer can be outrun by a quantum computer in 2019 using their 54-bit quantum chip Sycamore here. And later in 2020, a group of Chinese scientists again made a claim on quantum supremacy using their light-based quantum computer named Jiuzheng. But one more thing that I should tell you is that both these demonstrations have not been done for real-world problems that actually need to be solved. But these provide us with some hope that using ultra-fast quantum computing for real-world problems will one day become a reality, and hopefully soon. And here are some more recent advancements. IBM recently announced that they have built the largest quantum processor yet. Its name is Osprey. And one Osprey processor has 433 qubits, and IBM is hoping to put these quantum processors together in a kind of in a modular fashion and massively parallelize calculations, which sounds quite promising. And they're expecting to show us the new units later in 2023 in the Quantum Summit. And that's a little bit about the IBM's and Google's quantum processors. What I haven't told you about these processors is that all these computers need extremely cold environments to survive, because these quantum systems are systems that need ultra cold temperatures, or kelvins or millikelvin temperatures, to retain the coherence, which you will learn about in the later sessions. A German-Australian company called Quantum Brilliance recently announced the world's first room temperature quantum computer and installed it in a supercomputing center in Australia back in last year. And these computers are based on diamond chips, and these diamond chips have defects called nitrogen vacancy centers and 13 carbon spins. These diamond chip-based computers are still not as powerful as these Google and IBM machines. They still have only a small number of qubits working together in one cluster, but it's super nice to have quantum computers working in room temperature as well. So these are some recent developments in quantum computing around the world. Let's now have a quick look at the global landscape for quantum technologies as well. So many governments around the world are heavily focusing on quantum technologies. These governments include Australia, US, UK, many European countries like Germany, and countries like Canada, China, Japan, and Russia are also in the quantum race. And there are many companies popping up around the world focusing on quantum technologies, not just quantum computing, quantum sensing, quantum communication as well. And here's a bit of an overview of the patents and papers based on quantum technologies. They have been in a steady upward trend for about the past 30 years. So all in all, the picture seems to be quite promising, and it looks like a very good time for everyone to be learning a little bit of quantum computing and the basics of quantum technologies. And I hope that I have given everyone some motivation for today's workshop. And I hope everyone all the very best. Finally, I'd like to thank my supervisors, the affiliations, and the organizers of this workshop, and everyone for your kind attention as well. Thank you so much.
Thank you, Dr. Harini, for conducting that excellent session. I think that was a great keynote. You covered most of the important aspects we want to study today. So I'll go into the next session so that we can start digging into this subject. Yeah. Okay. I think my screen is visible right now.
Yes, Kithmin, you can see it.
Okay, thank you. Okay, so Dr. Harini gave sort of like a view of what quantum computing is today, all the cool applications it's going into, how fast the field is growing, and things like that. There's like a lot of questions people might be wondering about quantum computing, and one of the big things, how do you get into start like studying quantum computing, because it's quite a new field. I guess in the context of Sri Lanka, we don't have quantum computing in the university level. We don't study it yet, but definitely this is something that we could change in the coming years. And we have the means and the technology to do these things. And that's the sort of introduction that we want to provide today. And also to give you a realistic view of what is quantum computing today. Yeah, so let's get into it. First of all, I'd like to acknowledge the UBC Quantum Club. They have a really great organization, which is like very recently established, less than 2 years ago. And they have really expanded their portfolio and the work that they're doing. And partly this workshop is possible thanks to the support and the ideas that they gave on what to focus on, how to do this workshop, and how to sort of present this topic to a general audience. So you can check out their website as well if you're interested. So about myself, I'm a master's student in electrical and computer engineering. I'm also a graduate from ENTC. I was a previous lecturer and I was an alumni of the 15th batch. And right now I'm studying into silicon photonics, but quantum computing is something that's really up and coming in British Columbia, and something that goes very closely with the domain of silicon photonics as well. Right, so this was me probably 1 year ago. I was quite afraid to understand what a quantum computer was and didn't know what questions to ask as well. So probably some of you might be in the similar sort of situation. So please feel free to ask questions. Even all of us don't have all the knowledge on this topic, but we are also learning every day. So ask questions, don't be shy, and we'll try to answer as best as we can. We can't answer, we'll actually say we can't answer. So don't be shy. There's 2 interesting books that we want to present to you all on this topic. There's like a ton of other books, but definitely the interesting books for you to check out would be these 2 books. I think Dr. Subodha has personally read this book and recommended it. I have, I think all of us have here have read this particular book, and it's sort of the go-to book for quantum. It's called the Bible of quantum computing, actually. And probably every course that's taught in quantum computing refers to this book, I hope. And we also sent you some workshop resources through the email. So please use those resources as learning guides. There's a ton of other resources on the internet, but we just wanted to make it easy to find the right resources to get started. So that's the reason behind providing those. There were some optional prerequisites. Actually, I'll go into that after this slide. This is the GitHub page for the workshop. So I think we have provided the link for this page. Otherwise, you can find it under SkillSurf Introduction QC. And just to note, you can download all the content that we're doing today. Just go to code and then download zip, and you'll be able to access all the material. We'll be updating the final presentations here as well. So feel free to download everything after the workshop is concluded. Yes, there were prerequisites. So basically, I think when you're registering for this workshop, we sort of asked 2 questions: whether you have done linear algebra and whether you are proficient in Python. The reason was just simply because these 2 might be the kind of things that you might want to revise or just get a little good at in order to get started with quantum computing. So just a basic revision of linear algebra. You can use this Qiskit reference for doing some revision on that. And then about Python, just basics of iterating functions and understanding attributes and things. So there's a good summer workshop or summer school session by Qiskit which would be really helpful for getting started here as well. Okay, so this is the workshop agenda for today. As you know, there are 2 sessions. The first session is more theoretical with presentations and things. And then the second session is quite demonstrative in terms of hands-on examples, and we're covering 3 notebooks, if I remember correctly. And Teshani has done a great job preparing them. So definitely be there for the second session, because that's where the real application of this, what we are looking at, happens. So today, 3 instructors are here to help you, including myself. So this is me, and Ravi from Australia will be covering this first session, and then Teshani, currently in USA, will be covering the second session in the evening. Okay, so I would like to get started into my session. So it's not too long, but I want to do a small historical overview of this topic, and a really interesting overview it is. Yeah, so I think all of you recognize these 4 famous physicists, and they were sort of like probably like the big players of physics when physics was sort of falling into trouble, when classical mechanics couldn't explain some of the phenomenon that was happening around that time. And because of, like, we are actually lucky today because these people were alive at that time to actually discuss and understand and actually propose what the modern theory of modern quantum theory is now today. So you might not know about this story, but in 1941, this was after actually the World War had even started. Heisenberg, so this guy here, Heisenberg has visited Copenhagen in 1941 to meet Niels Bohr, his mentor actually, and they have sort of started discussions about what would lead to the atomic bomb project. And there's a big story behind that. There's actually nice movies made on this project as well, called the Manhattan Project. But anyways, this was sort of like the, I guess they call the birthplace of this topic, which the theories that led to this topic. And as you know, the father of classical mechanics is Isaac Newton, and his theories were beginning to fail at explaining certain phenomena, and people were looking for another another field which could explain the new observances that we were seeing, one of which you will actually get to see today. Ravi will be presenting that. So they came up with the theory of quantum mechanics, and it's basically governed by this. One of the things that's governing that is this particular equation called the Schrödinger equation, which is proposed by Erwin Schrödinger. And there are things called postulates. So quantum mechanics is based on these postulates, and these postulates they work. They've been tested, and they are the reason why we can define or like introduce a quantum state. And the quantum state is basically the status of something that is described using this theory of quantum mechanics that they developed, right? So that they came up to that point, and finally they like proposed this theory of quantum mechanics, or the quantum theory, which is currently like worshipped as the theory for explaining all that is weird and bizarre in this domain. And it works really well. It's been tested, and it's held up countless times against various tests. So that was quantum mechanics. Then how did it come to this quantum computing domain? So there were a few things that were missing in the mid 1900 era that actually happened to develop throughout the ages again. So some things like people started to observe the further galaxies and see systems that were in really cold temperatures, like very cold temperatures, close to absolute zero. And also they started to observe the effects of superconducting metals. And this is called the Meissner's effect. And superconducting metals are really, so theory of superconductivity is really great at being described using quantum mechanics. You can't describe it using classical mechanics. So this is sort of where things started to fall together. And you can like sort of, people like started picking up the pieces to connect these things together. And it really happened at the really nice, timely manner, because these are things that are like used right now to develop quantum computers. You have to like, as Dr. Harini mentioned, like cooling systems to millikelvin temperatures, like 5-10 millikelvin temperatures, and also building circuits out of superconducting metals. So these are things that are like really supportive to what we are benefiting from today. So with those things, people started to think about how to control single quantum systems. So previously at room temperatures, you couldn't deal with these things because of the huge amount of noise and everything. But now they started to think about, can we like achieve control over quantum systems? So this entire field of quantum mechanics was developed without thinking about this theory of quantum computing, but now they were starting to think about that. And the first real evidence that quantum computing, so most of you know that Alan Turing, there's this movie of him, Imitation Game as well. So Alan Turing is the father of the modern computing theory, right? So Alan Turing's, like the Turing machine was sort of like the universal, the theory of the universal computer. But could quantum computers actually challenge classical computing? So this was a question that was there for a long time, but then this scientist David Deutsch, he was able to actually show, like provide the first evidence that you could effectively solve a problem that you couldn't like, a problem that you couldn't effectively solve in a classical computer, you could do in a quantum computer efficiently. So that he was able to show that, and that sort of like led to the birth of this quantum computing field. So you'll actually be seeing an example of what these proposed. Tashani will be doing this during the second session. And then Peter Shaw, Love Grover, and various other groups actually came forward and came up with new types of algorithms that quantum computing could achieve supremacy over classical computing. So that really like led to the like it opened the possibilities for people to consider quantum computing as the next big thing in the computing era. And one big contribution was error correction, which was proposed by these three, I think, mathematicians, I guess. And they really enabled the modern quantum computers to be usable because of the fact that you can use error correction on quantum computers. And because quantum computers are really prone to noise, and therefore they could really be prone to errors. And with error correction, you can actually deal with any bit flips and things like that. And therefore, definitely, there's a potential for this to be used as a computer, like a computing device. And finally, this is the last, I guess, big milestone I wanted to cover. Last year, actually, probably 3 months ago, I guess, they awarded the Nobel Prize in Physics to experiments with entangled photons, the Bell inequality violation establishment, and finally, like this pioneering work done in quantum information science. So they say that Nobel Prizes are awarded for people who like do significant work in an area that has really impacted the entire world and the field itself. So therefore, they say that quantum computing would, like, this is sort of evidence that quantum computing is something that has really evolved during the past decade and would potentially change the way of how we do things going forward. So that there's a huge hope there. And we'll actually be seeing a little bit about entanglement and some demonstrations of that during the second session as well. So if you want to like learn a little bit about that, please do stick around for the second session. You'll get to see actually sort of like algorithms that like are being sent into actual quantum computer and getting results back and measurements and things like that. And you can do them yourself once you have seen how to do that. Okay, just a little bit more in my session, explaining qubits in brief. So I think Dr. Harini sort of showed you that this qubit, what the qubit is. Basically, in classical computing, there's this bit which can only exist in two states, on or off. Can be like 0 or 5 volts, low or high. So that's basically a two-state thing. So in quantum computing, there is this concept of superposition where the state can exist anywhere in between 1 and 0. And to see it in a better way, I think this is a more clearer demonstration. So the bit would only exist as 1 or 0, and you can depict it that way. But this qubit actually does not exist either at 1 or 0. It exists in this 3D sphere, and anywhere in this sphere, you can sort of like define the state of this bit as alpha times 0 and beta times 1. This actually means that this representation actually means that this entire sphere can hold the state of that bit between 1 and 0. It's sort of called the block sphere representation, as Dr. Harini's presentation mentioned. It's a kind of a tool to help us realize what this weird phenomena is. And you'll also see how the block sphere is changing these states and things in this is an IBM Qiskit demonstration. It's going to show you like how the block sphere representations and how we can alter the state of the qubit using different things called gates actually. Yeah. So any questions, please let me know. Basically, this block sphere is the mathematical or the visual representation of that mathematical identity I showed you for the state of the qubit. And the nice thing about qubits is that it exponentially increases your computing resources compared to a bit because of this superposition, because its ability to be in superposition. There's this great video on quantum computing from 2015 though, in Kurzgesagt. It's a really great YouTube channel, so please feel free to check it out. I won't play it here, but they have like a really good introduction to quantum computing and what it's all about. I've got some small parts from their video actually. So we'll just wait for the GIF to restart. So you know that our circuits have chips inside, and these chips are made. Chips basically are made out of modules, and these modules are made out of logic gates. Logic gates are basically transistors put together, and transistors basically allow the flow of current, so they sort of like control our ability to. Transistors are called like transfer resistors, so they allow us to do some control operation on the electrical currents that are flowing through our circuits. Now, so this is the classical mode of creating gates or operations on bits. And in quantum realm, you have to have similar kind of gates to control the state that I showed you. So the state of the block sphere kind of state. Now you have to have gates that if this NOT gate is turning this 1 into a 0, then this quantum NOT gate should be able to flip the state of this qubit. And similarly in this manner. So what's that all about? So this is kind of a example of some gates in the quantum realm. And I'll go through this diff again. So you can see in this example, this X gate is spinning the state around the y-axis, and the Y gate is spinning the state around the x-axis, and once more. And then the S gate is spinning the face of this state around the z-axis, right? So that's sort of a example of what gates are doing to quantum state or quantum bit. And even pushing that further, these classical gates we use to create circuits. So this is kind of a famous circuit in classical domain, and we can create circuits in the quantum realm as well. And so here's this circuit with 2 gates. These are called Hadamard gates, and then a C0 gate, and this is a 2-qubit gate, and there's like 3 qubits in this example. So, and then finally you do measurements. I'll go into this in the later slides. This just for representation purposes. And this is kind of a GIF to show you that you can sort of do some kind of gate-based manipulation on qubits by using these kinds of gates. And finally, once you measure the final state of the system, then it will collapse to these kinds of classical bits, right? So I don't think I need to go into detail into this, but there's a variation or between quantum and classical computing. And yeah, you can read about this later. But what I want to actually talk about is this important topic. I think most of you might be wondering, quantum computers are not here to replace classical computers. So that's a very important thing. So just to give you like the best overview, like this quantum computer won't be running your operating system, or you won't be putting this quantum computing chip inside your phone to control, like run your phone's operating systems, things like that. Because quantum computers are special purpose machines. They are sort of developed for specific purposes. I'll show you in the next slide. And we are interested in, so there's a sort of domain that is governed by classical computers and then quantum computers. And there's a sort of intersection region as well, but we are focused on quantum computers that are like fully quantum fully like quantum computing based, and these are special purpose machines actually. So that's sort of to give you an example. This is just a cartoon I added to tell you. I mean, like in one of the classes I was in, one person asked, "Can I watch movies on a quantum computer?" And there's no good answer for that right now. Like you can't play movies or TV series on a quantum computer, so that's not why it's being developed for. And right now, what do quantum computing chips look like? So there's all sorts of different qubits, too many actually. And this is a superconducting qubit. This is a trapped ion qubit, and these are photonic qubits I mentioned you earlier. And then Dr. Harini's presentation, she told you about diamond based NV qubits. So there's various types of qubits right now. And if you consider the IBM quantum computing chip that Dr. Harini mentioned, you can see that over the past few years, the number of qubits have been scaling on these quantum processors, even more than by double the amounts. And this is sort of like an image of the processor that Dr. Harini mentioned about. So it's got 433 qubits on it right now, and it's pretty good in terms of what they've achieved. I think this is the biggest quantum computing chip right now for general gate-based quantum computing. And in this roadmap, this is where we are right now, 2022, and they'll be releasing like even bigger versions of the quantum computing chips for this year and 2024 and so on. So really excited to see what's going to happen in this domain. And I think they have like really massive targets in terms of scaling quantum computing chips right now, so that they can sort of achieve I think 1 million qubit systems in good time. And this is sort of like a market survey that is being done in the world right now. It's a very highly valued industry. And with this amount of scale and integration of this much qubit or quantum power, you can see like fields like material design, drug design, financial services, and there are so many fields that will be like getting benefited from out of this technology and services. And this, I think also Dr. Hani mentioned, there's so many, and even medicine, right? So something to look forward to. And if you are interested, a great time to learn a little about this field. Probably if things go well, then like massive job opportunities would rise up for people who know a little bit about getting into this field. And the ecosystem right now. So this is sort of like kind of the ecosystem. There's end users, which probably we are not part of right now, but then universities in the middle help contribute to the development and these things. These are some of the famous companies that are in the field right now. And finally, the big players, the quantum technology developers are also here. Microsoft, IBM, Google, Intel, obviously. And there's like so many different approaches people are taking towards quantum computing. Yeah, one more slide. Quantum computing efforts worldwide. So you can see all over the world, like probably US has the highest, I guess. But you can see how much investment is being done in this field, and like how much China is the highest. How much they are investing in this field and trying to drive this technology forward. So yeah, I'm in Canada here, and I have like seen to my own eyes how much of a huge national investment. Even recently, they announced national um, funding program for quantum research. So yeah, that's the stage of that. So what to look forward to in this workshop? I just want to give you a small intro to what's coming up next. So this is sort of an image of three camera lenses placed one on top of each other. You can see something is weird here, and the explanation is even weirder than you think. And if you don't know the answer, Ravi will be providing you with a nice demonstration and approach to how to answer this. And don't be overwhelmed by anything you see. All of you have the means to understand everything on this domain. This was definitely like fundamentally developed as a mathematical theorem. So, but there are so many tools right now to understand this intuitively without like a less mathy approach, and we are here to provide you both of those resources. So we already shared you the notes. You can look on GitHub for those notes. And finally, there's a open source Python-based frameworks for quantum computing available. These are three famous ones: Qiskit, PennyLane, and Cirq. And these are the companies that are developing these three frameworks. And today we are going to go into IBM, which is probably the most famous out of these. And you're going to see what we can do with IBM, like look at some really nice examples. And hopefully you can pick up where to start learning yourself on these technologies and frameworks. Right, so I think that's the end of my session, and I'll be handing it over to Ravi to continue into the next session. So please go ahead and take over, Ravi.
Hello, hi. Okay, so let's begin my section. Okay, so can you guys see this?
Yes.
Yeah.
Yes, Ravi.
Okay, so about myself. So I am Ravi Wijesekara. I completed my PhD in Monash University 2 days ago. So I'm a brand new doctor. And before that, I was both working and learning at ENTC, so in University of Moratuwa. So like Dr. Harini before me, I am also coming in from a quantum physics background and not quite quantum computing background. So quantum physics is the hardware aspect of quantum computers. And so basically what I will try to explain in this short lecture will be, why do quantum computers work like the way they do, right? So that is what I am going to do. So this is a fairly difficult job. So this is an extremely highly mathematical subject. So just like classical computing is mostly mathematics, quantum computing is almost 100% pure mathematics. So this would be a pretty boring mathematics lecture, but I try to make it interesting with some real experiments and demonstrations. So my target is basically to show you what happens in the quantum realm and not just tell you what happens, right? So I want to demonstrate to you these quantum principles a little well. Okay, so I will be using Mathematica, a Mathematica notebook, and not a PowerPoint presentation, because I will tell you why. And think of it as a little bit of a new way of teaching, and we'll see how it goes. And this will be both my lecture note and my presentation. So the power of basically using Mathematica is that I can demonstrate some live animations of the concepts that I'm talking about. And also I can do the mathematics then and there and show you. So that is why I used Mathematica instead of PowerPoint. you can download the files. So you can download these files both in Mathematica form and in PDF form from our GitHub site. So if you take it from the PDF form, the demonstrations will obviously not work, but all the text will be still there. Okay, so what I want to do is understand, I want to make you understand what a qubit is. And to do that, I am going to use the polarization of light. So let us talk about what is the polarization of light in a classical model, right? So classically, a wave, light is basically a wave, right? So wave is basically a traveling oscillation in a medium or in the free space, right? So I hope you all know what a wave is, right? So there can be different types of waves. There are two main types of waves. So first one is what we call a longitudinal wave. So this is an example for this is a shock wave that is traveling in a slinky, right? So in this example, you will see that a wave is traveling from this side to the other side. So from the left to the right, a wave is traveling. But if you look at any one point in the slinky, that the particle in the slinky is moving in the same direction as the wave, right? So that is what we call a longitudinal wave, right? So an example is the shock wave in a slinky. Now the other side is a transverse wave. So let's take an example of a water wave traveling in a pond, right? So it will look like this. Now the wave is traveling radially outwards from the center, right? But if you look at any one point, the water molecules are going up and down, right? So that is what we call a transverse wave. So unlike longitudinal waves, transverse waves have a property called polarization. So what is polarization? So polarization means, now since our direction of travel is a vector, right? So you have one vector going like this. And I am saying that the molecules are vibrating in a perpendicular to that direction of motion. So what that means is there can be many perpendiculars, right? So if there is one line, one vector going like this is a perpendicular. This is also perpendicular. This is also perpendicular. So there are many perpendiculars, right? So exactly which perpendicular is the actual wave vibrating is the polarization of that plane wave, right? Okay, so let us come to light, right? So light is an electromagnetic wave in terms of classical physics. And in free space, it moves at the speed of light. And it has an electric field and a magnetic field that is perpendicular to each other. And both of them are perpendicular to the direction of the wave traveling, right? So basically, this is a transverse wave. And being a transverse wave, it has polarization. So in other words, polarization basically tells you in which direction does the electric field or the magnetic field point, right? So I have a small demonstration of it, right? So this is how an electromagnetic wave looks like when it is traveling, right? So it is traveling from the left side to the right side. And on the right side, we have the electric field. And over here, we have the magnetic field, right? So now, as you can see, the electric field is vibrating in the x-axis, right? So it is vibrating up and down. So what I will call that is vertically polarized, right? So that is the polarization of it. So which way is this vibrating, right? So this is what we call linearly polarized in the x direction, right? So these are the equations for the electric field and the magnetic field, right? So that is what we have plotted here. And so this is the actual equation. So this is the exact equation. And what you have is, so you have a direction, you have magnitude in the x direction, magnitude in the y direction, right? So those two things represent how big the vibration is in the x direction and the y direction. And there are two other terms, the phases, right? So the phase of the vibration, right? So probably those of you who have done electrical engineering are kind of familiar with this, right? Now, in this case, right? So we have the X amplitude, AX as 1 and AY as 0, right? So that will give you linear polarization in X, right? Now let us see what is linear polarization in Y-axis, right? So that means Y is equal to AY is 1 and AX is 0, and that will get you this, right? So it will be vibrating in the other plane. So previously it was vertical, now it is vibrating horizontal, right? So, but if you have, let's say, different dimensions, you can have, it can vibrate in other directions also, right? So you can have sideways polarized, right? It can be like this, it can be like this, it can be anything, right? So it can vibrate in different directions. And if we change the phases, right? So here, previously, we did not change theta y or theta x, but if you do change them, what would happen is it will it will vibrate in a kind of circular thing, right? So that is also a possibility, right? So this is called elliptical polarization because it looks like an ellipse when you look at from over here. But if you adjust it properly, you will see, okay, it is like a circle, right? And here also there are two states of happening, right? So this first one is called circular polarized clockwise, right? So this shows circular polarization clockwise because the electric field is kind of rotating in a clockwise direction. Now, if you had a different theta, right? If you change the direction, it would have vibrated in the other direction, right? So that is called circular polarized anticlockwise. Right? So there are different types of polarizations, right? So you can have X polarization, Y polarization, and 45 degrees, minus 45 degrees, anything, right? And even circular polarizations. So in every situation, the magnitude of the energy flow is basically the amount of energy that is carried by this wave is proportional to AX squared and AY squared. So that basically tells you how intense our light is. And the direction of energy flow is always given by E cross B. So it is going in the Z direction, right? Now we can represent this electric field as a polarization 2 vector, right? So what that means is in this thing, right? You know that the Z direction is 0. The electric field in the Z direction is 0 because it's a transverse wave. So you only have these two. And out of these two, I am not very interested in this, right? In the frequency of the wave, right? So I am not interested in that. So I am going to isolate only the magnitude and the phases. And then we can represent it as something like this. So you have a 2 vector, right? So this is a classical 2 vector. This is a classical complex 2 vector because this is a complex number, right? So this is quite similar to the phasor notation that we use in electrical engineering, right? Now, if you apply, let's say, the linear polarization, right? If you look at the polarization vector of a linear polarized X waveform, it will have AX not equal to 0. So this will be not equal to 0, but AY equal to 0, right? So this will be 0, right? So what we will have is a vector something like this, right? And if you ignore this phase, right? So we can have different vectors for different types of polarization. So there are 6 polarizations we can find for each one of them, right? So here we have that, right? So for the linear polarized in X, you have 1, 0 and e to the power ix, right? So that one, this ix comes out, right? Because it is 0, so we take it out. And we do the same. And then every time we try to take I theta y, the phase of the thing out of our vector, right? And then we will have, so for linear polarization in X, linear polarization in Y, circular polarization clockwise, circular polarization anticlockwise, linear polarization in a 45 degrees, right? So something like this. So you have linear polarization, so it's a line, but it is in the 45 degrees, and linear polarization in the minus 45 degrees, right? So for all of them, we can find different vectors, right? And in every one of them, I will take out this phase factor, and you can see some of them are complex vectors. So this is a real vector, but this guy has a complex number I over here. So that makes it a complex vector, right? and you can have something like this, right? So what I am doing is the polarization of light can be represented just by a complex 2 vector, right? So that is what I am going to, that's what I am saying, right? Okay, so now if you look at just the environment, right, you will see that always, yeah. So if you look at just light that is out here, right, they are basically unpolarized light, right? So that means it does not have a particular polarization, right? But if you send it through something called a linear polarization filter, it becomes a polarized light. So this is what a linear polarization filter looks like, right? And what it does is it takes unpolarized light and makes polarized light out of it, right? So conceptually, it works very simply. So what you have is basically conceptually, this is not what actually happens in here, right? Think of it as a mesh of wires, a vertical mesh of wires like this, right? Now think that an electric field, electromagnetic wave is coming into the monitor, right? So if the electric field is vibrating up and down, right, the electrons inside this wire will start to vibrate up and down because of that electric field. And because of that, a current will flow. And the wire will absorb energy from the electric field and waste it in the resistor. So what that means is an vertical electric field will get absorbed by this field. But if it is a horizontal electric field, then the electrons cannot move sideways because electrons cannot go out of the wire, right? So therefore, they do not vibrate and therefore it doesn't absorb, right? So what that means is after this light goes through this polarizer, you will be guaranteed that it will have only electric fields in the direction that is perpendicular to this wire mesh, right? And similarly, we can build circular polarizations, but since we are looking at the bare minimum, we are not going to consider that now, right? So what is my lecture plan, right? So I am going to do, first of all, I am going to do some practical experiments involving 3 linear polarizers, right? I have 3 linear polarizers over here, and I am going to show you some practical experiments. And the results will seem a little bit strange at first, but it will be very easily explainable using classical wave theory, right? Then I'm going to do it. So it is strange, but we have a classical kind of strangeness. Then I am going to reduce the intensity of light, right? In a thought experiment, I am not going to do it here. And we will go from classical light to quantum light, right? So from electromagnetic waves, I'm going to go to photon. And then I will try to explain again the same behaviors, but using the photon model, right? And what we will find is that the previous classical kind of strangeness will now become super strange, ultra pro max kind of strange, right? And that strangeness is quantum mechanical. It is not classical, right? And from that, I will say, okay, polarization is a quantum bit and try to explain what a quantum bit exactly is, right? And then I will introduce the mathematics inside these quantum bits, right? So in this way, I will probably hopefully individually, I will try to explain why the mathematics of qubits looks like the way they do, right? Okay, so the first experiment that I am going to do, right? I am going to send random light, right? So some kind of light, and I am going to send it through a vertical polarizer, right? So what that means is so assume that what this lines means is if it is a vertical polarizer, only vertically polarized light goes to the next side. Okay? So you have both directions over here. So vertical component and a horizontal component. So the polarization vector looks like this. But after you go through this one, what will happen is this part, the horizontal part will get cancelled and you get only a vertical polarization, right? And I'm going to send it through another vertical polarizer, right? What will you observe, right? So from the first one to the second one, because I am dropping half of the energy, right? I am dropping the half, the horizontal part or portion of the energy. So you will see a 50% reduction in intensity. But in the second one, because it is already vertically polarized, right? So the second filter does not have anything to block, right? It is already, what is there to block is already gone, right? So therefore you will not see a reduction in intensity, right? So I will show you, right? So basically, without the filter, I look like this, but when I put the filter, you will see that my the image is a little bit darker, right? And I'm going to put the second filter in the same configuration as the first filter, and you will see that, okay, so you can see, right? There is not much of a difference between the 2 points. It's a little bit dark, but that is due to the filter itself being not perfect, right? But you can see most of the light is, you can still see me, right? So that is the first experiment, right? Now, in the second experiment, I am going to have 2 linear polarizers which are 90 degrees apart, right? So the first polarizer is vertical, the second is horizontal, right? So what will we observe, right? So what should happen is the first filter will only send out the vertically polarized light, and the second one will destroy all vertically polarized light. So what we should get is basically 0 coming out, right? So you should not be able to see anything, right? So I will do the experiment, right? So at the beginning, I am aligned, right? And now I am going to turn this 90 degrees, right? And as you can see, when it is completely 90 degrees, you do not see anything, right? Everything is blocked, right? But if I turn it back, you see, you will begin to see me again, right? So that is the second experiment, right? So please remember these experiments, right? So the first one, when both of them are parallel, 50% comes out. If they are perpendicular to each other, nothing comes out, right? Okay, so now I am going to do another experiment, right? So in this experiment, I am going to basically put another filter, which I call filter I, right? So filter A, filter B, and in between those filters, I am going to put another filter, and that filter is arranged at 45 degrees, right? So first one is vertical, next one is 45 degrees, and the third one is horizontal. So what would be the output intensity in this case, right? So I'm going to take the 2 filters like this. So and I am going to put them in the configuration of 90 degrees, right? Like this. And so you can't see anything, right? And what I'm going to do is I'm going to take a third filter and put it in between, right? So what will be the observation? So can you please take a minute to think about it and put it in the chat? Out of these 5 answers, what do you think will be the intensity that is coming out at the end? Okay, so we have one answer, A. So please just don't worry about anything. I'm not going to mark you on this, right? So just think about something and just tell me an answer. Just do a guess. Okay, 12.5. Any other guesses? C. Okay, another one. B. Okay, Kithmin says B. Okay, so let me set up the experiment, right? So what I'm going to do is, first of all, I don't have 3 hands to handle one, right? So I'm going to put this into the camera, right? So now you can see. So the first filter is inside the camera. And so I'm going to put it in, so the second one, right? So the second one is at 90 degrees, right? And I'm going to take the third one and I'm going to put it in the correct angle. And I'm going to put that in, right? Okay, now the angle is correct, right? So do you see that it is not 0%, right? Something comes out, right? If you don't have the filter, there is nothing coming out. If you have the filter, you see something, right? So definitely it is not answer 0. right? So not A, right? And it actually turns out the correct answer is 12.5, right? So, but A is an intuitive answer, right? Because filter A still removes all the horizontal line, filter B removes all the vertical line, so therefore nothing should be left, right? Even if filter I does something in there, right? But that is not the case, right? So I will show you why, right? So what will happen is, what we will actually observe is 100% comes through at the beginning. So out of them, 50% is left in the first stage, and then out of them 50% will be left in the other stage. So that will be 25%, and then half of that will go through the last stage, right? So why does that happen, right? So this is how the mathematics of a polarizer works, right? So if you have a certain polarization vector coming in, right, which we will call A in, right? So that is this vector P, right? So basically at the B, so I will say if this is the one, it will break that into two perpendicular, the parallel section to the polarizer and the perpendicular section to the polarizer. So it will break it into two 90 degrees components, and the parallel component will be let through, the perpendicular component will be deleted, right? So basically at the beginning, so you have both, and then the horizontal component gets deleted and 50% comes in, right? And this one is a 45 degrees, right? So our polarization vector is at 45, is vertically, right? Because this light is polarized and that is vertically polarized. So you have vertical, and then you have to take components to this one and this one, right? And that will give you, so 1 is the length here, right? So that will give you 1 over square root of 2 and 1 over square root of 2 in both directions, right? And this one, so the one component will get deleted. This component will get deleted, right? And this will be left. So 1 over square root 2 in this direction, right? And now we have to take, so to make the vector again, you have to take 45 degrees again, right? The components, the vertical and horizontal components, you have to take another sine 45 degrees or cos 45 degrees, and that will give you half, right? So therefore, the polarization vector that comes out from this guy will be 0.511, right? And from that vector will go inside the next one, and that guy will delete the vertical part, and then you will get this one, right? So the polarization vector will be 0.5 coming out, right? Okay. Now I am going to do the same experiment, right? So this was the down here is the previous experiment. It was, our angle was at plus 45 degrees, right? And I am going to do the minus 45 degrees one, right? Obviously, you will see that it's the same thing, right? You will have 12.5 intensity going out, right? But when you go through the mathematics, you will see that the vectors are actually a little bit different, right? So when you do the same mathematics that you did here and apply it over here, you will see that the vector coming out is not half and half, but half and minus half, right? So here it was half and half, here it is half and minus half, right? So basically the horizontal component is in the opposite direction, right? So you can see clearly in the two images, right? The difference, right? And then we will cancel out this guy, right? So this guy will, the filter B will cancel out the vertical component, and you will have 0.5 and minus 1, right? So here we had plus 1 and here we have minus 1, right? So now I am going to do a fourth experiment, a thought experiment, right? I am going to insert something called an all-pass filter in between, right? So what does this all-pass filter do, right? So it is buildable, right? But I don't have the technology to do it right now, right? So think of it as something a wizard gave me, right? So what an all-pass filter does is it takes the incoming light, right? And it takes this component, right? This particular component, the plus 45 component and minus 45 component, it separates out those two components, right? And the plus 45 component is led through a plus 45 degree filter, and a minus 45 component is led through a minus 45 filter, right? Since they are already filled, so we are sending a plus 45 into a plus 45 filter a plus 45 polarized light. So therefore it doesn't do anything, right? So this guy doesn't do anything, this guy doesn't do anything, and we are sending them back together, and another wizard basically combines them together and sends it through, right? So what we have done is basically do nothing, right? So this is a filter that does nothing, right? So if you have this in this setup, it doesn't do anything, right? So basically what I'm trying to do is I'm going to look at a filter that is letting through all the light, right? So that is what I'm trying to create, right? Now, understand that this process of separating, filtering, and recombining doesn't do anything at the end, right? This will become critical later on, right? Now, if we block one way, if we block this filter with a paper, right, with a piece of paper, I put a piece of paper over here, right? What would happen is this will become a plus 45 filter. Now, if you put a paper on the other one, it will become a minus 45 filter, right? So we can recreate the two experiments before, right? So now, if we insert an all-pass filter, right, what would happen, right? So this is basically experiment number 2, right? Because the all-pass filter doesn't do anything, right? So in experiment 2 also, right? So we didn't have a filter, right? So all-pass filter is equivalent to having no filter, right? So therefore, it should be 0 intensity coming out, right? So what you can see here is 0 intensity, right? So this is made up of 2 filters, right? So what actually happens is, right? So the path that is going from the top filter, which is this kind of light, right? And the part going to the bottom filter, this kind of light, basically adds together and interferes, right? They make an interference. And because of that, so basically if you look at the 2 vectors, plus half in the second component comes from the top one, minus half comes from the bottom one, and both of them add together and make 0, right? So that is how the 1, 0 comes, right? So if you add this vector and this vector, it will become 1, 0, right? So in the other case, you have 0.5, 0, 1. So 0 and half in the first part. So in the top one, in the bottom one, you have 0 and minus 1, and they may combine together and make 0, right? So that is why you don't get any intensity outside, right? So this is interference of light, right? So this is the interference property of waves, right? It happens because classically electric and magnetic fields are vector components, right? They have 2 components and they add like vectors, right? So we only considered linear polarization here. So that is why we only had real vectors, right? So 1, 0, 1, 1, right? Vectors like that. But if you had the circular polarizations also included, this would have been complex 2D vectors, right? As we saw earlier, right? So do you understand everything, right? And do you have any questions, right? So I will, if you want, I will give you a little bit of rest, 1 minute, 2 minute rest, right? Try to understand what I say, right? If you have any questions, you can ask me, or if not, you don't have anything to do, you can look at how the mathematics works, right? Okay. Okay, so basically in this one, I'm just basically saying that if we have an angled polarizer, which is angle theta, right? So what is the component that will be let through and what will be deleted, right? So you have AX in, AY in, and the components in this direction. So this is the let through one, right? So that will turn out to be AX in cos theta because it is the inside angle, and AY sin theta because it is the outside angle, right? So this is the component that is going out, right? So if you look at them as vectors, right? So that is the first part, right? So that is the first part of the calculation. The second part is because we are looking at the horizontal and vertical components of it, so we have to take this one and cos theta again, right? So AX out will be this multiplied by cos theta, and that will give you this answer. And AY, the y component of this vector, is you have to sin theta it again, right? And that will give you this answer, right? And then you can write it as a matrix, right? So this will be cos squared theta times ax times sine cos times ay, right? I think that's pretty enough simple, right? Okay, so that is the classical picture, right? So everything good up until now? I hope so. If you have any questions, I don't see any questions, so I am assuming that things are okay, right? So you can either ask in the chat or you can unmute yourself and ask if you have any questions, right? So this is the classical model. Right? Okay, so now things are going to get a little bit more difficult, right? So I am going to look now at the quantum picture, right? So the classical picture was that classical theory was that light was an electromagnetic wave, right? So, but to see the true nature of light, we have to look at light at very low intensities, right? So I will propose another thought experiment to look at how it's going to happen, right? So I'm not going to do the experiment, but I'm going to show you the results, right? Okay, so you have a very dark room, right? So I'm going to turn off all the lights and I have a single color laser light, right? So I have a laser light like this, right? Okay, I have a laser light and then I have a sensor, right? So I'm going to turn on the laser light at t equals 0 and I am going to turn on the sensor at t equals 0, right? What the sensor does is it measures the total light energy that fall upon it since it started, right? So I'm going to start both the laser and the sensor at t equals 0, right? And I'm going to plot the sensor reading with time, right? So what you will see something like this, right? So as the time goes on, the amount of energy absorbed is linearly increasing, right? And that will depend on the amount of energy and the intensity of the laser, right? But it will be definitely a line, right? Now I am going to decrease. So in this one, number of packets per second, but what that does is basically decreases the intensity of the light, right? So now we are absorbing 5,000, right? So I'm going to decrease. Now we are absorbing 4,000 and I'm going to decrease again. So 3,000, 2,500, 2,000, like this, I'm going to decrease, right? Now, as you can see, as we are going into smaller and smaller pieces, right? So at high intensities, it is linear with time, right? But when it is, the intensity is low, right? Okay, this is not lambda, this is n, right? A little bit of a mistake. Right. So when I'm going to decrease n, it is randomly varied, right? Now I'm going to decrease a lot, right? So now you will see, okay, it is not linear at all, it is random, right? And it looks like a staircase, right? Okay, so this one, okay, not easy to adjust it. Okay, yeah. So the width of the staircase is randomly varied, right? So you have big step over here, small step over here, very tiny step over here. Right? Okay, I will get you even smaller. Right? It will look like this, right? So big steps, small steps, very small steps, right? The width of the staircase is varying, but the height of the staircase will always be the same value, right? So what that means is, right? So the step height means how much energy are you absorbing at a time, right? And that is always fixed, right? So the time it comes, the width of this thing is random, but the height is always the same. So every time it is being absorbed, the amount of energy that is being absorbed is kind of the same thing, right? So can this height change? Right? It can change, but only if we change the frequency or the color of the light, right? So if we change the light frequency and check the step heights, right? What we will get is we will get this relationship, right? So that is the relationship that Einstein found, right? So energy is proportional to the frequency of the light, right? Not anything else, not the intensity of light, right? But the frequency of light, right? So that gave us the quantum theory of light. So just like water is made up of molecules, right? Light is made up of energy carriers, which we call photons, right? And each photon carries an h omega amount of energy, right? So this h omega value, right? The value itself is not important, but that depends only on the frequency of the light, right? Not the source of the light, the intensity of the light, or the measuring instrument, or where in the universe we are doing the experiment, right? Even if you go to Andromeda galaxy, you will see the same value, right? And the energy is absorbed or emitted only in integer quantities of this H omega, right? So you don't have, so basically one quanta, one H omega, we call a photon, right? We don't have half photons, quarter photons, or anything else, right? Okay, so in the quantum theory of light, light is a particle and it is not a wave, right? Okay, so I'm going to try to explain the same experiments that I did earlier, right, with quantum photon theory, right? So what has changed? The intensity of the incoming light is reduced until only one photon is inside the system at any one time, right? So it is a very low intensity light, right? And instead of measuring light intensity, we are going to count the photons, the number of photons that we find in each of those stages, right? And we will keep doing the experiment until 1,000 photons go into the experiment, right? So instead of waves of light, we have particles of light, right? So for now, we will assume that this light particle is very much like a classical particle, right? So we can think of it as just a rubber ball coming in, right? And to match with this new particle theory, right, each photon should have its own polarization variable. So each ball has to have its own sense of its polarization, right? Because why? Because each photon enters the system alone, right? So therefore, each photon must know its polarization, right? And what the polarization filter does is when it comes in, the filter is going to look at the photon's polarization variable and decides whether to let it pass or not, right? So each filter is a test of the photon's polarization, right? So in the first case, right? So in the first experiment, 1,000 photons come in, right? And so we know these numbers, right? 1,000, 500, 500, that comes from the intensity, right? So from the early experiment, we know that half the photons go to the next stage and all the photons go to the next stage, right? So we are simply checking not the results of the experiment, but we are checking the interpretation, right? That is all we are doing, right? So 1,000 comes in. So filter A looks at those thousands and filter A fails half the photons, right? So only 500 goes through the next stage, right? And filter B does the same test, right? Because it is the same direction, it is doing the same test, right? So a photon that passed the test once will pass the same test again, right? So 500 photons will exit the next one, right? So very simple, right? So from that we build a rule, right? A photon that passes a test will always pass another test which is parallel to it, right? So therefore, you have an internally consistent definition of polarization, right? Okay. In the 90-degree case, 500 comes through, nothing goes out, right? So therefore, every photon that pass filter A's test will fail filter B's test, right? So if a photon passes filter A's test, it will not pass filter B's test, right? So none of the photons will exist filter B, right? So from that, we make the second rule. A photon that passes a test will never pass an immediate test which is perpendicular to, right? So we can have this in different directions also, right? So not just vertical and horizontal. Even if you have plus 45 degrees and minus 45 degrees, it will still be the same, right? So if a photon passes the plus 45 degree filter, it will not pass the minus 45 filter, right? Or minus 45 filter, right? Like that. Okay, so what that means is it can be either horizontally polarized or vertically polarized, not both, right? A single photon cannot be both polarizations at the same time, right? Because then it will pass both tests, right? So either vertical or horizontal, right? One or the other. So we can generalize it. So we can say it is either theta polarized or theta plus or minus 90 polarized, right? So that's the same angle, but we are just, instead of this, I'm considering something like this, right? Okay. So now the real question, right? So look at the two experiment number 3, right? So you have 45 degrees plus 45 degrees and minus 45 degrees, right? So what happens is 500 pass the first level, 250 pass the second level, 125 pass the third level, right? That is the same on the other one also. So plus 45 minus 45 doesn't make a difference in the number of photons that is going through, right? But now we know from rule 2 that whatever passed this polarizer will not pass this polarizer, right? So therefore, if let's say out of this 500, the 250 photons that passed over here, right, will not have passed this test, right? So therefore, we can color these 500 photons either blue or purple, depending on whether it passes plus 45 or minus 45, right? So in the first place, so out of those 500 photons, we can say, okay, 250 of them are blue, and those blue are the guys that pass through the first one. And out of them, another 125 passes the next one, right? So in the bottom one, we have 250 purple ones, and those pass the second one, and out of them 125 pass the last one, right? So that is what this says, right? But A and B are mutually exclusive, right? Because a blue photon cannot pass over here, right? Because of the 90-degree rule, right? And the purple photon cannot pass in the other case, right? So therefore, these are mutually exclusive photon sets, right? Okay, now I am going to ask the mind-boggling question, right? If we send both of them through, right, what would be the output, right? So basically, our common sense will say, okay, so blue photons, out of the blue photons, 125 went through. Out of the purple photons, 125 went through, right? But if we let them both, then we will have something like this. Both of them will be there, right? And because of that, 250 has to pass the next one, right? Do you get that? Okay. But what actually happens is 0 passes, right? So what did the all pass filter do, right? So if you have the all pass filter, we know from the previous results that 0 passes, right, at the end, right? So that is what the classical explanation told us, right? So what the all pass filter did was, it basically took these filters, took the photons, the blue photons went the top way, and it didn't do anything to the photons, right? It didn't change the photons in any way, and they came back and went. The purple ones took the bottom route and came back and went, right? So basically, the same set that came in here comes out, right? So now, how come none of the things pass when we set both of them through, right? So I will have another little bit of an interval to wrap our heads around this, right? So basically this is the crux of the matter, right? I know that some of you, or even most of you, may not have understood everything, right? But that is why I'm giving you the note, so you can think about it on your own, right? But think about it, and for now, right? And think what is the problem over here, right? So basically, it's like 2 doors, right? So the blue ones only go through the top door, the purple ones only go through the bottom door, right? So the thing that has to happen is, right, so if you leave the other door open, let's consider a blue photon, right? If you let the other door open, right, so then the blue photon will not travel to the other one, right? Because none of the blue photons pass the filter B's test, right? So he has to know. So in the case where this one is open, the blue photon has to know that he has to fail filter B's test, right? But if this is closed, right? If this is closed, then that is this case, right? In that case, the blue photon has to know that it must pass filter B's test 50% of the time, right? So in one case, so I am considering 2 cases, right? So case 1, where both upper and lower filters are open, right? So that means the filter is an all-pass filter, right? One of these, right? In the case 2, I am going to assume that the lower filter is closed with a paper, right? So that means this is this case, right? So in case 1, because it is an all-pass filter, the photon, the blue photon, right? One of these blue photons must know that he has to fail the test always, right? In case 2, the photon must know. So in this case, in the plus 45 degree thing, it has to know that it must pass the test 50% of the time, right? So how does the blue photon that has never even visited the lower filter, right? It doesn't go through the lower filter, right? But how does it know whether the lower filter was closed or not, right? He doesn't even go through that door and he doesn't even see the door, right? But still, he knows whether that door is open or not, right? So that is the problem, right? That is the whole problem of this whole thing, right? Okay, so so because of the time limitation, I'm going to go quickly, right? So I'm going to look at some counter arguments that you might come up with, right? And some responses to them, right? So all this happened, right? Because only one photon was in the experiment at the same time, right? Now, since H omega is very small, so this is a counter argument, right? So this is something that you might say, right? So since H omega is so small, maybe it is not physically possible to have only one photon, right? Maybe there is always multiple photons, right? And maybe in experiment 4, right? In the experiment of the all-pass filter over here, right? A blue photon and a purple photon always goes in pairs, right? So like a girlfriend, boyfriend kind of thing, right? So one goes through the top one, the other goes through the bottom one. And when they come back together, they talk to each other. And the purple one, so if the purple one came back, right? Then the blue one knows, okay, she came back. So therefore, the door must have been open, right? And from that, he can figure out whether do I pass the exam or not pass the exam, right? So that might be an alternative theory, right? But that doesn't work because photons very rarely interact with each other, right? So if you have, let's say, 2 water hoses, right? And if you cross their streams, right, like this, what would happen is water will flow every which way, right? Why? Because the water molecules hit each other, right? But if you have 2 laser beams crossed like this, right? Does something like that happen? Does the light go here and there, right? No, it just passes through, doesn't happen, nothing happens, right? So what that means is, even though there are multiple photons, right? Even if there were multiple photons, they do not interact with each other, right? So therefore, even if we have a high intensity light, right? Even if there were multiple photons inside the experiment, they will not interact with each other, right? So essentially, each photon can be considered to be in there all alone, right? So it doesn't do anything. So that explanation doesn't work, right? Okay, another one can say, okay, another one of you can say, okay, but at least we know how it works classically, right? So therefore we can think, okay, so we can just forget all this and go back to the classical model and it worked perfectly. So it might work now also, right? But that also doesn't work, right? Why? Because vector operations that we did with the electric fields, right? Adding the horizontal components and the vertical components, right? That only worked because their components were continuous variables, right? So basically we had a photon like this, right? So not a photon, electromagnetic wave, right? And when you send it through a vertical polarizer, it generated this one, right? So 1, 1 became 1, 0, right? Now the energy is the square of this. So the energy was 2 in this case, but it became 1 in the other case, right? So energy halved, right? So even if there was 1 photon and it worked in this electron as a wave, right? Its energy would have been halved, right? But in the photon model, if you use a photon model, right? If we halve the intensity, then the color has to change. Sorry, if we halve the energy, the color has to change, right? Because of that H omega relationship. But the color doesn't change in any of these, right? So therefore, the energy doesn't change, right? The energy is the square of the electric field. So therefore, electric field has to not change also, right? So even if you measure the electric field at different points in a single photon, it still will give you the same value as before, right? So there is no half electric fields, right? So therefore, that model also doesn't work, right? So this is the mind-boggling question of quantum mechanics, right? So many people were extremely uncomfortable with this. Most of all, Einstein, right? It is his theory, right? But even he, almost until the time he died, did not accept his own theory, right? So they were very uncomfortable with it, and they tried so much to build other models, other explanations for this behavior, right? What is the behavior? A blue photon going in one door still knows what the other door tells you, right? So the only possible explanation that they found out over the whole 100 years of the history of quantum mechanics is that a single photon actually travels both paths at the same time, right? So even if there is, so basically our model, we saying that the blue photon only travels this path is false, right? It is not like a ball that travel only one path, right? A single photon can travel both paths at the same time, right? So that is not a classical object, right? So it is like a magical thing, right? So when you have a ball at the beginning, but that ball kind of separates out into a ghost ball and another ghost ball, and those ghost balls go through the two filters and combine together again, right? So that is what actually happens, right? So the true nature of a quantum particle, like a photon, is that it is both a particle, so it is like a ball, but a wave also, right? It is not a ball, it is a ball and not a ball, right? And if you measure it, the moment we measure it, it becomes a particle. When you absorb it, when you emit it, it is like a particle. But as soon as, if you don't measure it, or it is traveling all along, it goes as a wave, right? So now this wave is not an electromagnetic wave, right? A photon is not an electromagnetic wave. So it is something strange. It is what we call a quantum wave function, right? It is a wave, but it is not a wave in the electrical field or the magnetic field, right? And what happens is, if you square the wave function, you will get a probability function, right? So before measuring, the photon exists as a distributed quantum wave function. So it is going in every direction and it is everywhere at the same time, right? But when you measure it, it will randomly appear in a single location, right? And that the probability of appearance at any one given location will be given by the square of the wave function at that location, right? So previously we understood that we have an electric field, right? When you square it, we get the intensity, right? Here we have a quantum wave function, and when you square it, you get the probability of appearance, right? So that is actually what happens, right? So basically what happens is, instead of the electric field or the electromagnetic wave, right, what we have is a quantum wave function, and it goes like a wave in all directions in both filters at the same time, and it interferes like a wave, right? And because of that interference, it can go multiple paths as they want, right? So basically, instead of an electric field going like this, we have a wave function, right? And instead of a polarization vector, we have something called the qubit state, right? So this is the qubit state, right? Now, just like the electric field works as vectors, as they add like vectors and they operate as vectors, the wave function acts as a vector, right? So the mathematics are basically the same mathematics, right? So you have 1, 1, and then half of it is gone. So you have 1, 0, and then it comes through two paths, right? One path is half, half, the other path is half minus half. And when you add them together, you get 1, 0. And then of that vector, half of it is cancelled. So no vertical parts, right? So therefore you have 0, 0. So 0, 1 and 0, minus 1, right? So sorry, 0, half in the first case and 0, minus half in the second case. And when you cancel them up together, nothing comes and goes through, right? So the mathematics works exactly the same as an electric field, right? Not the electric field, the polarization field, the polarization vector, right? This P vector, right? So that is what happens, right? So now I hope you understand what is actually going on, right? So what I will tell you is now you already know what the mathematics is, right? So then I am going to formalize that mathematics into a certain setup, right? So that is the final part of my lecture, right? And I think I am on time. Yeah, so I will take about another 15 minutes or something. Okay. So now we already know the mathematics, right? We understand what is going on, right? But now what we are going to do is we are going to put them in a mathematical form, right? So using postulates, right? Okay, so for those who don't know what a postulate is something that we use in mathematics, right? And what the meaning of postulates is, it's a postulate is something that we take without argument, right? We take that as the basis of it. So basically the most basic postulate of mathematics is 1 + 1 is equal to 2, right? We don't ask why 1 + 1 is equal to 2, right? So it's the same thing, right? So basically this is like a formalization of the things that we already knew, right? So a single quantum bit is described by a complex 2 vector, right? So just like the polarization vector that we used earlier, right? And multiplying such a vector by a phase, it doesn't represent the same state. So that is a caveat. That's an important point, but let's keep it for now, right? The norm of all valid vectors should be 1, right? So that means this is 1, 1, right? So when you square it, if you square this one and add them up, you should get 1, right? So here you have 2, right? So this vector is not correct, right? So you need a square root of 2, 1 over square root of 2 at the beginning to make it correct, right? So this one is wrong, right? But on all the others, you will see 1, 0. So that is 1 squared plus 0 squared is 1. So that is okay. This is half. So half squared is half squared plus half squared. So that this part all alone is wrong, but when you add them up, you will still have the same structure, right? So this one is correct, and this one is also correct after you add them up, not the individual ones, right? Okay, so I will tell you why that is, right? So basically, we introduce a new notation, right? Which we call like this, right? So we represent a qubit like this. So this is called a ket, right? So this symbol is called a ket, and there is another symbol which is similar to it, right? So you have this symbol and a very similar symbol, and we call this a bra, right? A bra vector is the complex conjugate of the ket vector, right? So ket vector is like a row vector, column vector, right? It is represented like something like this, right? And if you want to take the bra vector of this ket vector, you have to take the complex conjugate of it, right? So basically, AB is still the same, but the plus I theta V becomes minus I theta V, right? And both of them together, a bra vector, this bra vector and a ket vector together combines into a bracket, right? So that is why this bra and ket came from, right? And it makes something like this, right? And that is called the inner product of the row and column vectors, right? So basically you can multiply a row vector and a column vector together, right? And from that you will get a single scalar quantity, right? Something like this, right? So that is called the inner product of the vector, right? And the inner product of a vector with itself should always be 1, right? So if you apply that to this particular vector, you will see that it will give you AB squared plus AH squared, right? And that should be 1, right? So that is basically saying that for any quantum state, this has to be 1, right? So it should be, it's something called a normalized vector, right? In linear algebra, you would call it like that, right? So to represent the vertical quantum state, I'm going to use this one, right? So these 6 vectors we already learned earlier, right? So these came from the polarization, the plus 45, minus 45, those kind of polarization, right? So vertical polarization was 1, 0 from the previous lecture note, and horizontal was 0, 1 from the previous one, right? And plus 45 was 1 over square root 2, 1, 1, right? We already know that. And this one also. And there is the 2 things that we didn't consider were the circular polarizations, and they would look like this, right? You can take my word for it, right? Okay, and the second postulate is basically what happens. So this is how a quantum state exists, right? But what happens when you observe that quantum state, right? So what happens when you do a measurement, right? Or observe it, or do a test, right? So in the filters, I use the word test everywhere, right? And wave function collapse, right? Those are kind of the same words, right? But what happens is each measurement, so a measurement like that is represented by a Hermitian 2x2 matrix, right? So Hermitian is a mathematical term, right? It's a kind of matrix, right? That's the only thing you have to talk about, right? If it is a Hermitian matrix, it will have 2 eigenvectors, right? A 2x2 Hermitian matrix will always have 2 eigenvectors, right? So 2 vectors, E1 and E2, which we will call them E1 and E2, right? And 2 real eigenvalues that are corresponding to it, right? So E1 and E2, right? So this is why at the beginning we told that we need a little bit of linear algebra, right? Okay, so now let's say you do the measurement M, right, which is described by this matrix on a qubit state phi, right? What would happen is what you will get is a random answer, right? So you will either get E1 or E2 as the answer. When you measure it, you will either get E1 as the measured value or E2 as the measured value, right? And if you want to find out the probability of getting E1 or E2, what you have to do is take the inner product of the qubit state with the eigenstate and then square it, right? And that will give you the exact value, the probability of getting that value, right? And the other one, for the E2 measurement, you will have this one, right? Now assume that you measured E1, right? So if the measurement was E1, then the previous quantum state will be erased and it will be replaced by a new quantum state, and it will be E1, right? So that is what it tells us, right? And then so you can take this as a given, right? So I will say that the matrix for a linear polarizer at angle theta is given by this particular matrix, right? So if you look at the eigenvectors and eigenvalues of this matrix, you will find out that they come up like this, right? So this is why I use Mathematica, right? So this is a Mathematica command, and that will give you the eigenvectors and eigenvalues, right? So this one is not normalized, and this one is also not normalized, because if you sum them up, it will not be equal to 1, right? So you have to normalize them by adding a factor, right? And when you do that, you will find out that these are the 2 eigenvalues for that thing, right? So for a linear polarizer, these are the 2 eigenvalues, right? So I will explain what a linear polarizer does, right? So it measures and observes what the polarization of the photon is, right? So it looks at the wave function and observe what that value is, right? So basically it is doing a test, right? And that the result of the test comes randomly, right? As I told, right? Now, if the test gives E2, that means +1, right? So if the test gave +1, it will let the photon pass, right? And the probability of passing is given by this one, right? And the state of the photon will now be not phi, not whatever came out, right? But because it is E2 was observed, the photon that goes out will be E2, right? And if the photon originally gave -1 as the result, then it will absorb the photon, and the fail probability is this, right? And the moment the test occurs, the previous wave function will be deleted and a new wave function will take its place if if the test is passed. So if you pass, that is what will happen, right? So that is basically the mathematics of how it happens, right? So this is a little exercise, right? So I will not go through it, right? So I understand that you will not, you did not probably understand everything that I said in the last section, right? So please go through it on your own, in your own time, right? And this is a little bit of exercise, and you will find out that, okay, everything works if we use these mathematical techniques, right? So what happens is, if you mesh, so basically what happens inside is simply what I told you, right? So as long as you don't measure a photon, right, it goes in different ways. But when you measure it, random values comes out and the wave function resets to a new value, right? And yeah, so that is if you measure it, right? Now, there is the third postulate where you can say that if you don't measure anything, right, the wave function will not collapse, right? So the wave function can evolve or change without actually measuring it. If you don't measure it, it can change, right? The wave function can do interesting stuff, right? So for example, in the all pass filter, right? In the all pass filter, what we did was we send it through without doing anything, right? We didn't measure it, right? Because we did not absorb anything, right? Because measuring means, testing means we have to either absorb the other, pass the other, something like that, right? But in the all pass filter, we did not do such a thing, right? So that is kind of an operation that actually did not do any measurements, right? Another one is if you rotate the whole setup, right? So if you have the, let's say, three things like this, right? And let's say you have the 2, 4 things, and I rotate the whole thing together, right? Then the results don't change, right? So something like that is also a unitary evolution, right? So those kinds of things, that means the experiments that don't do measurements, right, are called unitary evolutions, right? And they are represented by unitary matrices, right? So a unitary matrix is another mathematical term, right? And what happens is, so it is something like this, right? So a 2 by 2 matrix that has so a unit matrix or matrix that looks like a unit matrix, right? So this one is also kind of a unitary matrix, right? So for the all pass filter, the thing is the unitary matrix is the unit matrix, right? For rotating all 3 polarizers, right? So this one, for this example, the unitary matrix would be something like this, right? So what happens is when you do that kind of evolution, right, without measuring, what happens is the previous state, which was, let's say, vertical, right, vertical polarization, right? Once you do the unitary evolution, what you have to do is just multiply the previous vector with the matrix, right? And then you will get another vector, right? So that is just like modifying the state, right? And so let's say if theta was equal to 90, right, in this particular case, right? So then when you do it, it will become 0, 1. So that means it has become the horizontal state, right, like this, right? So unitarily evolving a vertical polarizer can give you a horizontal polarizer, right? So this is what in the future you will learn, that this is what a quantum gate is, right? Okay, so basically this is the summary, right? So you can have in the classical picture, you had an electric field, right? And that added like vectors, and intensity, which was the square of the electric field, was what we measured, right? So that is what the classical model was, right? In the quantum model, we have a quantum wave function, right? It looks like electric field, but not quite, right? And what it does is, when you square it, you will get the probability of appearance, right? and each photon carries a certain fixed amount of energy, right? So therefore, if you take this probability distribution and do this experiment for like millions and billions of photons, this will recreate this classical intensity picture, right? So that is what actually happens in these slides and everything, right? Because there are billions of photons coming in, right? Each of them has a probability distribution, but since there are billions of them, we are testing it again and again and again. And therefore, you get an intensity. So this probability wave function, probability function gets converted into an intensity function, right? Okay, so yeah, I think, taken more than my time. So I will go through the next few steps very quickly, right? So this was photon. So we looked at polarization of a photon, and that was a qubit, right? But there are other qubits also, right? The spin of an electron is a qubit also, right? So in A-level chemistry, you might have learned about principal quantum numbers, right? Orbital angular momentum quantum number, so N, L, M, and S, right? And in the case of, so these are not qubits, they are more complicated entities like this, than that, right, than a qubit, but S is a qubit, right? So the spin of a photon is actually a qubit, right? So instead of polarization, we are measuring the spin of a qubit, right? So, and they also look very similar, right? So you have very similar structures to that, right? But the thing with photon was that it almost never interacts with another photon, right? Two laser beams, if you cross it, nothing happens, right? So they just pass through each other. So they don't interact, right? But if you cross two electron beams, some of them will hit each other, right? So they can actually interact with each other, right? So electron spins can actually interact with other electron spins, unlike photons. And therefore, spins can be used to build interacting multi-qubit systems, right? So therefore, we are not limited to this two bit structure, right? So what that means is, let's say you have a single qubit is represented by a complex 2 vector, right? Single qubit 2 vector, right? And any measurement on them is a 2 by 2 matrix, right? So you have this type and this type, right? But if there are two qubits, right? So you can have something like this, right? So qubit number A, it has these states, and a qubit B, which has other states, right? And both of them together can create 4 possible states, right? Because one can be this guy, and so you can have vertical polarized, vertical polarized. Vertical polarized, the other guy is horizontally polarized. The first one is horizontally polarized, the second one is vertically polarized, and both of them are horizontally polarized, right? So there are 4 possible states, right? So for a 1 qubit, you need a 2 vector, complex 2 vector to represent its polarization. If you have 2 photons, you will need 4 vector, a complex 4 vector to represent its polarization, right? So if we had 3 qubits, you need 8 complex 8 vectors, right? So you need 8 numbers in here, right? If there were 4 photons, you need 16 numbers, and so on and so forth, right? So if you have 2 qubits, then basically you need a 4 by 4 matrix to represent what occurs inside that, right? So in the end, right, what happens is when you have multiple qubits, right, the amount of the vector space required to describe them increases exponentially, right? So a 1 qubit needs a 2 vector space, complex 2 vector, 2 qubits need a complex 4 vector, right? Now a single qubit, a single photon, so a 2 vector, we already saw that it can go in 2 different paths at the same time, right? A complex 4 vector similarly can go in 4 different paths at the same time, right? And a complex 8 vector, right? So basically a complex, so 3 qubits, that is a complex 8 vector, can go in 8 different paths at the same time, right? And so on and so forth, right? So we can build, if you have multi-qubit systems, right? Not photons, but think of them as electron spins, right? They can go just like a photon went in two paths, right? These electrons can go in multiple paths at the same time, right? And the more electrons we have together, right, the more paths they can travel, right? Okay, so that brings us to the almost the end of the lecture, right? So I will have a little bit of final comments, right? So we learned a lot about qubits, right? So why is this qubit not a classical bit? So that is the first question that anyone can ask, right? Well, because it is not a 0 or 1 thing, right? Because it is a complex 2 vector, right? So therefore, you need two complex numbers to describe this, right? So bit is just 1 or 0, right? So this has so much more information than a classical bit, right? So that is why it is not a classical bit, right? Polarization of a photon is not a classical bit, right? Why? Because of that, right? Okay, then why is this a bit, right? So this is an extremely complicated thing. So why are we saying that this is a bit, right? Because at the end, we cannot measure the qubit without erasing it, right? So if you measure the qubit, it erases, right? So therefore, what we can get out of any measurement is either this or that, right? So one of two values, right? So in our polarization case, it was simply that did it pass the polarizer or did it fail passing the polarizer, right? So even though there is a lot of information inside, we can't actually access all of them at the end, right? So only one bit of information goes out, right? Inside there's lots of information, but what goes out is just one bit. Now, how does this help to create quantum computers, right? So we knew that one photon can travel two paths, right? And we understood that that 3 qubits can travel 8 different paths like this, right? So it can travel 8 different paths at the same time, right? Now, if you think about those 8 different paths as doing calculations, right? Each path is a sort of calculation, right? So a classical computer can calculate the first path first, and then he had to recalculate the second path, third path, fourth path, like that, right? But a photon can go all the paths at the same time, right? And simply do all the calculations in just one go, right? So that is the power of a quantum computer. So if you have n qubits, right, perfectly working n qubits, it can go in 2 to the power n different paths at the same time, and it can do 2 to the power n calculations at once, right? So that is why quantum computing is very powerful, right? But the limit is that even though it goes through all these paths, right, what comes out at the end is just a answer, 1 or 0 answer, right? So I told you, right, there's lots of information in the middle, but we cannot access all of them at the same time, right? We cannot access all of them. Only a bit of information can be taken up, right? So therefore, even though it can do all the calculations inside at the same time, we cannot extract all of them. So we have an exponential speed up, but it is not as easy as it sounds, right? Because we need very specific algorithms to make sure that that one bit, the small amount of information that we can actually extract solves our problem, right? So that is why quantum computing is difficult, right? So not a lot of algorithms are there actually, right? Because we have to figure out a way to actually do this, right? So those algorithms, it cannot run any algorithm, right? You have to have only a very specific algorithm that can be run on a quantum computer. And that is why we cannot have quantum computers in our computers, right? Because not all algorithms will work, only some algorithms. Okay, so with that, I will finish it. So if you have any questions, you can ask, or we can move on to the next one. I hope it was useful, right? You may not have understood everything, but what I want to tell you is to go through the lecture note again, right, on your own and try to understand what is going on. Okay, thank you very much. I think I took more time than necessary. So I'm very sorry for Kithmin because he will have to do it fast, his session. And yeah, with that, I will finish. Thank you.
Thank you so much, Ravi. I think that was an excellent introduction to covering the mathematics and the ideas. Definitely, it was worth the time. Even I enjoyed it, learned a lot of new things. So no worries. I think there's 30 minutes left for the first session, and I think that's just about enough time for me to go through this last part. And then we'll have a small break, and we'll be doing the hands-on session. I definitely encourage all of you to attend that because that's one of the most, actually the most important part about getting into quantum computing once you know the theory. So I just have a few slides here. So I just want to talk to all of you about the journey of a quantum algorithm, and I'll sort of focus on a small aspect of that journey to describe this. So sorry, I think I'm on the first slide. Let me just go to, okay, can you all see this slide on the quantum journey? I hope.
Yeah.
Okay, thank you. So this, I'm just adding this link to the LinkedIn and the Twitter pages of this company called IQM Quantum Computers. I find them that they share a lot of like nice details about quantum computing technology and theory, and found a lot of the resources helpful. I'm referring to two of them here. This is the first one. So it's kind of like nice to look at the journey of a quantum algorithm, right? So, you know, if you ever get into this field, you start thinking about a quantum computing problem that you want to solve. So how does this go through the process, right? So this is actually how it happens. So you think of the problem, you code it in Qiskit, I guess. So some Python code like Tashani is going to do today. And it's going to then send, the code is going to represent your circuit in this, in a form of like quantum circuits, which is what we're going to look at today. And then it's going to sort of transpile this code, and it's going to start to send it into a quantum computer. So there's a compilation process, and then it's going to first travel to the server, and then some compilation process, and then it's actually going to go into your quantum computer, and then inside the chip, which is this like this thing hanging down like that. And once it's processed inside the chip, then it's going to get measured out, which Ravi explained, and then the results are going to be sent back to your computer through the server, and then you're going to look at the results. So everything in this process, Tashani is going to demonstrate today. It's very cool, and everything happens within not milliseconds, maybe milliseconds or seconds of time. So there, I was showing you the quantum circuit, right? I was pointing this arrow to this quantum circuit. So this quantum circuit has few things that we need to set up in order to make it work. So you need the initializations and the resets and things. So you have your qubits, you initialize from some of the qubits, and then some of them you reset them into zero state. You have your quantum gates. This is a circuit that you build that you want to test. So it can be entangling stuff like that, and other like complex gates as well. Then you do measurement, and you basically sort of fold the state of the, or like make the state of the qubit fall into a classical bit. So you classically capture the state of the qubits, and then you also can have like classically controlled gates. So these gates, based on whether this state is 1 or 0, these gates can classically control this qubit which was not measured. So there's like different techniques you need to understand as well as do for working with quantum algorithms, and it's really neat, and everything's there for you to study. This just to show an idea of this, like below GIF, I guess, is trying to like show you what this concept of a quantum gate is. So it does look like a weird thing that I can't explain what it is here. But essentially, if you actually look at it, as Ravi said, these are essentially matrices. And these matrices, like in its nature, it's kind of a matrix. And the matrix you can multiply with the state of the qubit, and then you get some output, which is the output state of the qubit. There's someone raised the hand. Do you want to ask a question? Or if you want, you can unmute and ask. Yeah, please feel free to interrupt me if you need a question. So there's 6 kinds of single qubit gates. This is the Hadamard, 3 Pauli gates, X, Y, and Z, in honor of Wolfgang Pauli. And then 2 phase gates called the S gate and the 5x8 or the T gate. And this is kind of to show you that these gates are built on the quantum computing chip, and then that's how it travels through the quantum computer, through the servers and everything onto your computer, right? So I'll do a small interactive session. So this, starting with the Pauli gate, we can look at each of these gates, and the Pauli gate is pretty easy to understand. So that matrix there, this Pauli matrix, so it's actually the opposite of the identity matrix. You know, the identity matrix is a diagonal matrix with 2 like ones on the diagonal, but this is flipped, right? So basically the Pauli gate is flipping the state, initial state, to the opposite state. So if it's a 0 state, it's going to make it a 1. And if it's a 1 state, it's going to make it a 0. So it's a pretty simple analogy to a NOT gate that we know from electrical or the logic gate design. And then like I'll go into the rest of the single qubit gates. So let me get out of this screen. Isn't that happening? Sorry. So there's this notebook here that I've linked. So that was the Pauli X gate, and I'm going to share this link with all of you so you can follow along with me. Okay, so this is the Pauli X gate, and the Pauli X gate, we said converts a 0 state into a 1 state. So you can open up this interactive GUI, and right now we are looking at the 1 state, right? So you can see that the probability of, so not the 1 state, sorry, the 0 state. So we're looking at the 0 state. So it's the 0 state right now. This is the 1 state. This is the 0 state. So it's now 100% probability of the state being the 1 state, and this 0% of being the 0 state. If it's the 1 state, then there's 100% probability of it being the 1 state and 0 for the 0 state, and there's no phase. Okay, so this is also a probability meter. Now just apply the X gate. So you can see the X gate is flipping the state of the qubit. That's you can clearly see, right? So that's the single qubit X gate. And it's converting the state to the opposite state. Now there's this Y gate, the Pauli Y gate. So the Pauli Y gate also does the same flipping, but there's a phase conversion as well. So you can apply. So you can see the phase mentioned in the bottom. So the Pauli Y gate does the flipping, but also changes the phase by 5/2. Right? So the Pauli Z gate. The Pauli Z gate does not actually change 1 to 0, but it takes a different state called this plus state. So if you look at this plus state, so plus state is kind of probability of half for 0 and 1. It's kind of like a middle state, 0.5 for 0 state, 0.5 for 1 state. So it's in this state now. So Z is going to flip both the phase and the state from plus to minus. So you can see it's going from plus to minus. Sorry, something happened. So yeah, it's going from plus to minus, right? That's the Z gate. But if we apply the Z gate to the 0 state, nothing happens, right? So I hope that was clear. So Z state is only flipping plus to minus, but at the 0 state, nothing happens. At the 1 state, it's only flipping the phase. So that's one gate. That's a separate kind of gate. Now the Hadamard is a very interesting gate. I think it's a very important one as well. Yeah, it's very important because often we need to scramble. So this gate allows us to do entanglement. So let's try the Hadamard gate. So Hadamard actually flips 0 to plus. So you can guess if it's at 1, what happens when you put the Hadamard gate? Can anyone guess? So it shifts 0 state to plus. So probably 1 state to minus, right? So that's what the Hadamard gate is doing. So these all 4 gates we covered. So Hadamard gate flips 0 state to plus. So like 0 state to a state which is half of 0 and 1, and it fits one state, again half of 0 and 1, but opposite phase. So that's a very neat gate. And then 2 more gates. These gates are called phase gates because they don't do any state flipping in terms of like, so if we look at this one, so if it's the Hadamard gate, so it only flips the phase, right? So this one flips the phase by 5/2, but T gate flips by 5/4, right? And this plus sign is for opposite direction. So it is going in the opposite direction. It just means that this is reversible, right? So you can go back and forth. It's reversible. So T gate is a phase gate, and also the S gate is a phase gate. And the nice thing about single qubit gates is these gates are reversible. And that's a requirement in quantum computing. All the single qubit gates have to be reversible in order to like do these quantum computing operations. And for example, if you apply the Pauli gate twice, you undo what you did with one gate, and it's obvious here. So if you apply the same gate twice, it's undoing what you did. See, for all the examples, Hadamard, everything. Same thing twice undoes what you did. So that's the basic idea about single qubit gates. And I'll stop the interactive session from there. And one thing to note is you can compound gates because these gates are matrices, right? So if you multiply three of these matrices together, and if you get another matrix, so in this case, if you multiply H, Z, H, you will get X given here. And that means that, so if you give H, Z, H, so I gave 0, so H, Z, H. So that's the one state, right? So it says it's equal to X. So actually, if I try that, yeah, so I can get the one state. Phase is different, but still I can get the one state by doing that operation. So this is kind of how you write quantum algorithms. You give your state, you write your gates, and that is equal to the compounded gate. There's something else called 2-qubit gates and multi-qubit gates as well. So if you want to use more than 1 qubit in your circuit, then you can add more qubit lines. So essentially we have qubit gates up to 433 qubits now. So you can use multi-qubit gates in these new processors coming up. And there are a few different types of 2-qubit gates, right? We'll be going through these gates in the hands-on session. So this is the gate that we require for doing entanglement. And these are the different types of gates that we use to get the Bell states. So the Bell states are important because these are sort of like related to the Nobel Prize ideas as well. It's not the same thing, but essentially the idea is that the Hadamard gate and 2-qubit gates allow us to get like entangled states. Entangled states are like two different qubits are sort of entangled to each other, right? Like this. So this Alice state and Bob state, you send them into a Hadamard gate, and then you can send them to a C0 gate. So this is a matrix like that. This is a matrix like this. And out of this, you get this entangled state. So it's Alice and Bobcat in one state, one set here, and opposite of Alice and Bobcat in the this state here. So 0, 0, 1, 1, but it's probability of half. So it's entangled. And there's some nice simulators available that you can use to do simulations like multi-qubit gate simulations. So this is one, IBM Quantum Composer. So you can check that out. It's also available. We won't be doing it today, but it's a nice thing for you to check out. And then this one also available. It's an open source one for drag and drop quantum computing circuits. It's pretty nice. I haven't used it much, but feel free to check it out. And a few more slides. So I'll quickly wrap up with the last slides here. Okay. Yeah. So the dream of quantum computing is actually to achieve a universal quantum computer. And we discussed this question that right now you can see that the number of qubits are scaling, right? Scaling in even an exponential way. And this is kind of like the difficult challenge that people want to achieve in terms of like getting a machine with more than 100,000 physical qubits. And it's going to impact a lot of different fields. And even though it requires a very high computational power, it will definitely like transform industries as we know it. And this is like the true grand challenge of quantum computing. It's very hard to develop compared to the currently developed quantum computers, quantum annealers and analog quantum computers. And finally, just a small detail about measurements as we go into the hands-on session. So in the measurements, as Ravi explained, this is how you represent a measurement in a quantum circuit. And essentially in the measurement, you're basically collapsing this quantum state into a classical bit. So you don't know the state, whether it's a 1 or a 0, what it is right now. But after you measure it, you get some measurement so that the state has collapsed and you can't recover it anymore. And finally, just a small background about noise. So all these technological advancements we are doing, like bringing quantum computers down to this sub-Kelvin temperatures, like huge machines, like supercomputer-sized machines built with lots of EM protection, like electromagnetic protections, and that funny shape of the quantum computers you've seen, like it's coming down like a some kind of like a chandelier. So all these things are to protect qubits in your quantum computer from noise, because noise is the main enemy of like keeping like quantum computers from like actually being achievable much better than they are right now. So and people have really innovated a lot in order to go past this challenge of noise in quantum computers, because if we have noise in quantum computers, which is very easy to introduce, then noise is going to accumulate in your quantum computer until it's going to like create an avalanche of errors, and it's basically garbage in the end instead of like useful information. So we have to avoid noise in quantum computers. And the nice things that were developed in the past, most recent, like last decade, I guess, was quantum error correction and techniques of sort of introducing like building circuits that could do error correction. And this has really helped to sort of address like fault tolerant quantum computing techniques. And definitely it has allowed people to develop hardware to a somewhat extent, like below a certain threshold of noise tolerance, you can build the hardware. And since you have error tolerant techniques to address error correction, then software can then come in and fix the errors and make quantum computers useful. So modern quantum computing definitely relies on both the hardware that they've like really innovated to reduce all this noise, and then really good algorithms and error correcting techniques to come in and play a role with making quantum computers useful, right? So that is kind of the holy grail right now. And finally, just one last slide. This is a nice cheat sheet for you to keep with you to refer to any of these terms that we taught you today. So qubits and bits, 1 qubit gates, 2 qubit or multi-qubit gates, and like small block diagrams and things. And definitely keep learning about these concepts. Nielsen and Chuang is the best place to go. And there's many more resources out there right now. So we'll take a break now. since we are at 12 o'clock, and we can come back in an hour at 1 p.m. and we can do the hands-on session, which will be really interesting. And you'll get to study about Qiskit, how as a user you can get into using Qiskit as a developer, and then getting your results and things like that. Okay, thank you so much, and you enjoyed today's session. And thank you, Dr. Harini, Dr. Ranga, Dr. Subodha, and Ravi for being very generous to present throughout this session, and for staying for the past 3 hours.
Kithmin, so we are getting back together at 1 p.m., right? In an hour?
Yes, we can get back together at 1 p.m. exactly in an hour.
Okay.
Okay, yeah, we'll end the session for now, right?
Yes, yes. After lunch, we'll gather again in an hour. Right?
Okay, okay. Okay, see you everyone. Thank you.
Thank you.
Yeah.
Bye.